Computer science is no more about computers than astronomy is about telescopes. All right, I know I left you hanging last video. Hoping you were coming back for the last one. All right, so where do we stand? So basically, if we think in terms of what we know about asymptotics, we showed that the MCSS problem is big O of n cubed, right? We gave an n cubed algorithm. And it's actually pretty easy to show that a problem is big O of some function. Just come up with an algorithm and analyze it, right? The best algorithm is no slower than that. So we would say that n cubed is an upper bound on the best algorithm for MCSS, right? Now the question is n cubed a lower bound on this? Or is MCSS big omega of n cubed? Well, so showing a lower bound on a problem's complexity is a little bit tougher, right? So how do you prove that it's impossible to solve it more quickly than you can? Well, one of two things is true, right? Either you do that work of showing that it's impossible to solve it, or you actually go ahead and find a faster algorithm, right? So is there any way to speed up this algorithm? You better believe it. There's a huge there's a huge thing that you can do. If we think about how the algorithm works, we're computing this sum from I to j. And if we think about it, at some point, say we have I and we have j, and we have some values here. We have 5, 3, blah 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 up to 10. We have all this sum here. Maybe the sum at this point is like maybe 50. There's a -3 in there. I don't know. And then we basically throw this sum away, and then we increment j to be the next thing here, and maybe there's some value here, -3 or something, and then we recompute this sum. We go through the whole thing again and find that this sum is 47, right? Why do that, right? You already have the sum. Just go ahead and add the next thing on. So instead of needing a triply nested loop, right, we really only need a doubly nested loop, right? So in this case, we initialize the sum, and as we're looping, we add on this sum, right, and just add on one element at a time, and we're still going to check to see if it's bigger than the max. All right, what is the big O runtime of this guy, right? Going from 0 to n-1, and this guy goes from I to n-1. And I'm not going to resolve this right now, but if you look back to what we've done in Classify, this is incredibly similar to selection sort that we did on the first day, and it turns out that it is big theta of n squared. Okay, and the runtime was about 1/2 n squared, right? So that's way better, right? So again, let's go back to our recap here. So now we just showed that the problem is actually big O of n squared, right? The n squared is an upper bound on the runtime of the most efficient algorithm for it. Now the question is, can you do better than n squared, or is n squared a lower bound? Again, showing a lower bound, you either show that it's impossible to solve in faster than n squared time, or you find a yet faster algorithm. Okay. So then the question is, what if such an algorithm exists? What is it? Can we do better, right? And I'll say tune in next time for the exciting conclusion, right? We will take a look at this. I want you to finish up your quiz right now. And next class, we are going to talk about yet faster ones. And actually, in this course, we're going to be talking about 2 different faster ones that are faster than n squared. So any sort of intuitions that you had as you were coming up with this about ways that were better than brute force, you're going to be able to unleash them next class and start to turn that into an algorithm. All right? Come back next time. See ya.